3. I/Atlas is already on its way out, not circling back, not settling into orbit, just cutting through the dark after giving us one brief, impossible look at material from another star system. For a few months, this object turned the solar system into a crime scene, and every telescope became a witness. It was the third confirmed interstellar object ever found, after Oumuamua and Borisov, but it did not behave like a simple repeat. It arrived with dust, gas, strange chemistry, changing brightness, and a trail of questions behind it. The more we watched, the less ordinary it became. The first discovery alert came in July 2025 from the Atlas survey. At first, it was another fast-moving point of light. Then the orbit was calculated. Hyperbolic. Unbound. Not born here. That one detail changed everything about the object in the frame. It was never a danger to Earth. Its closest approach to our planet stayed far beyond any panic scenario. But scientifically, it was close enough to matter. Close enough for spacecraft, solar observatories, ground telescopes, and infrared instruments to take turns pulling secrets from its coma. And just when the story should have been ending, 3 I/Atlas did the most useful thing a cosmic visitor can do. It changed. It brightened. It pulsed. It threw off material. It made itself easier to study at the exact moment we thought the best observations were behind us. The last months were the dramatic ones. As it moved away from perihelion and toward its closest approach to Earth, the comet began to show activity that felt almost staged for astronomers. A body from interstellar space, briefly warmed by our sun, started shedding evidence in every direction. Late in 2025, observers reported a sharp increase in brightness. To a casual viewer, that sounds like a comet simply getting prettier. To scientists, it means fresh material was exposed, ice was breaking open, and buried chemistry was suddenly being thrown into space. The outburst did not just make a brighter dot. It built a larger target around the nucleus, a swelling halo of dust and gas. That halo became a laboratory. Solar particles could strike it. Molecules could break apart. Emissions could be measured from a distance. That is what made the moment so valuable. We were not only watching ice sublimate, we were watching the stored ingredients of another planetary system react to our sun. For a short time, our solar system became the test chamber for matter that formed somewhere else. The stranger the data became, the louder the speculation got. But mystery is not the same as evidence for aliens. The strange part was not that 3 I/Atlas was artificial. The strange part was that nature had built something this informative, then sent it across interstellar space by accident. The real story was better than the rumor. Every new measurement pointed back to formation conditions we cannot visit directly. Ratios of gases, dust behavior, rotation, jets, brightness changes. These are not decorations. They are the fingerprints of a birthplace older and farther away than the sun. Then came the signal astronomers had been waiting for, an X-ray glow. Comets from our own solar system can glow in X-rays when their escaping gas meets the solar wind. But catching that from an interstellar comet is something else entirely. The process is called charge exchange. Fast solar wind ions slam into neutral atoms in the comet's coma, steal electrons, and release energy as X-rays. It sounds microscopic, but around a comet, the effect can write a visible signature across thousands of kilometers. The outburst made that possible. A thin coma gives the solar wind too little to hit. A dense coma becomes a screen. 3 I/Atlas briefly inflated that screen, and suddenly the invisible interaction between the sun and an interstellar body had a shape. What made the data even more interesting was the chemistry. Observations from multiple instruments pointed toward unusual abundances, especially carbon-rich behavior compared with many familiar solar system comets. That does not make it impossible. It makes it foreign in the most literal sense. Think of every telescope as asking the comet a different question. Infrared instruments asked what molecules were warm. Ultraviolet instruments asked what atoms were glowing. Optical telescopes asked how dust scattered sunlight. X-ray instruments asked how the solar wind was colliding with the coma, and the comet answered by falling apart slowly, which is exactly what comets do best. They leak. They vent. They spin. They reveal layers that had been sealed away for billions of years. The destruction is the data. For researchers, the X-ray halo was not just a visual oddity. It helped connect the comet's gas production to the changing conditions around the sun. The same solar wind that shapes Earth's auroras was now lighting up matter from beyond the solar system. That is the scale of this event. Not a rock passing by. A temporary laboratory moving at interstellar speed. It entered, heated, reacted, and left, carrying most of its story away again. We had to read the parts that escaped while they were still glowing. Under all that gas, the nucleus remained the hardest thing to measure. A comet's coma is like fog around a headlight. It tells you something is there, but it also hides the shape. Early size estimates spread across a huge range because the solid core was buried inside its own activity. Then the brightness began to pulse, not randomly, rhythmically. As jets rotated into and out of view, the comet's light rose and fell like a slow heartbeat. Every peak and dip was a clue to the spin of the nucleus beneath the haze. Before perihelion, the rotation period was measured at a little over 16 hours. After the close passage by the sun, the period shifted. Not dramatically enough to tear the comet apart, but enough to show that the object was being physically changed by its own outgassing. That is the strange beauty of comet physics. A jet is not only a plume, it is a tiny thruster. Gas escapes from one side, and the nucleus receives a push in the other direction. Over time, those pushes can change how the entire body spins. So 3I/Atlas was not simply being observed, it was being altered in real time. Sunlight heated it. Volatiles escaped. Jets pushed on the body. The spin changed. The coma brightened. The visitor was reacting to us as much as we were reacting to it. The size question mattered because it changed the stakes. A small nucleus losing that much material is fragile and intense. A large one is more stable and massive. For months, estimates ranged widely, from hundreds of meters to several kilometers. Then geometry helped. When Earth, the Sun, and the comet lined up in a favorable way, the viewing angle reduced some of the confusion from scattered light. It was not magic. It was timing. And in astronomy, timing can become a new instrument. The improved observations pushed the story toward a compact nucleus wrapped in a spectacular coma. That contrast is what made 3I/Atlas so dramatic. The solid object may have been modest, but the environment it generated around itself was enormous. Dust and gas do not behave the same way. Dust reflects sunlight and drifts under radiation pressure. Gas fluoresces, reacts, and traces different forces. Separating those signals is how scientists turn a fuzzy spot into a physical object. To see structure, researchers used processing methods that suppress the smooth coma and reveal what is uneven. Once that bright fog was reduced, the comet stopped looking like a blur and started looking like a machine with vents. 4 jets stood out. One stronger sunward feature and 3 smaller jets arranged with surprising spacing. The symmetry caught attention because nature rarely arranges a messy active comet in a way that looks that clean from our point of view. But symmetry can mislead. A rotating irregular body, seen from one angle, can produce patterns that look deliberate. The job is not to be impressed too quickly. The job is to ask what surface vents, spin, and viewing geometry could produce that pattern naturally. No spacecraft landed on 3 I/Atlas. No probe sampled its ice. Yet the jets gave us a rough map of active regions on its surface. Each plume was a pointer aimed back at a place where sunlight had found volatile material. That matters because an interstellar comet is not just old ice. It is stored architecture from another planetary disk. The way its surface responds to heat tells us how that material was layered, damaged, irradiated, and preserved during a journey through interstellar space. The best part is that Earth was not alone in watching. While ground observers lost clean access near the Sun, spacecraft scattered across the solar system became unexpected witnesses. They were not launched for this visitor, but they were perfectly placed to catch it. This is opportunistic astronomy at its finest. You do not get years to design a mission to an object that arrives without warning. You use what is already out there: cameras, spectrographs, solar probes, planetary missions. Anything with the right angle becomes part of the network. Europa Clipper became one of those witnesses. Built for Jupiter's icy moon, it found itself in a position to observe another icy body from interstellar space. Its ultraviolet spectrograph saw the comet from a geometry Earth could not match. The value was not just distance, it was perspective. Europa Clipper viewed one side of the comet while another spacecraft saw another. That meant scientists could compare scattered dust and glowing gas from different hemispheres, almost like lighting a sculpture from 2 sides. Ultraviolet observations detected emissions tied to atoms released when sunlight broke apart escaping molecules. Hydrogen, oxygen, and carbon became clues, not because they are exotic by themselves, but because their ratios reveal how this comet's ice compared with the comets we know. That comparison is the point. Solar system comets are leftovers from our own construction site. 3 I/Atlas came from someone else's. If its carbon behavior, water release, or dust response differs, it gives us a sample of how planet building varies across the galaxy. By the midpoint, the story changes scale. The first half is the object itself, the outburst, halo, heartbeat, size, and jets. The second half is the network around it: spacecraft, archives, galactic history, and what this visitor tells us about the next one. Then came JUICE. ESAs. Jupiter Icy Moons Explorer was also designed for the outer solar system, not for a surprise interstellar encounter. But the timing was almost absurdly useful. In November 2025, JUICE had the right instruments, the right geometry, and very little time. Normally, deep space observations are planned on long schedules. This one had to be compressed. Teams refined the comet's path, checked spacecraft constraints, and built an observation campaign while the target was still changing. The whole operation became a rehearsal in fast science. Calculations placed JUICE among the closest spacecraft to 3 I/Atlas after perihelion. Its closest approach was about 0.4 astronomical units, roughly 60 million kilometers. That is not close like a flyby, but for an interstellar comet, it was an extraordinary feat. JUICE used 5 instruments to take measurements: cameras, spectrometers, and particle sensors built for icy moons, but suddenly pointed at interstellar ice. That is the kind of scientific improvisation that changes a mission from a single-purpose tool into a solar system observatory. There was a catch. JUICE could not immediately send everything home. After the campaign, the data sat on board until the spacecraft could safely turn back for a high-rate downlink. For months, one of the rarest data sets in comet science was literally waiting in memory. When the downlink finally arrived in February 2026, it came through long, deep space passes. Images and measurements moved across millions of kilometers at the speed of light, turning delayed photons into fresh science. A comet already leaving was still producing discoveries. Together, JUICE and Europa Clipper gave researchers something unusually powerful: simultaneous views of different sides of the coma. One side showed more scattered dust. The other emphasized glowing gas. For once, the comet was not a flat picture. It was a three-dimensional event. Those observations strengthened the picture of a carbon-rich visitor. The exact interpretation will keep evolving, but the direction is clear. 3I/Atlas was not a perfect twin of local comets. Its recipe carried the imprint of another disk around another star. For the spacecraft teams, this was bonus science. For planetary science, it was a stress test of our readiness. The next interstellar object will not wait for a dedicated mission either. 3I/Atlas showed that a prepared fleet can become a net. NASA's Parker Solar Probe also joined the story from a brutal vantage point near the Sun. Built to survive heat and solar particles, Parker watched the comet from a place Earth-based telescopes could never occupy. Its images were not glamour shots. They were geometry. Over repeated observations, Parker's view helped track the comet against the changing solar environment. For an object whose activity depended on heating and solar wind, that context mattered. The Sun was not just a light source, it was part of the experiment. Then Tess added another twist. The exoplanet hunter had unknowingly seen 3I/Atlas before its official discovery, hidden inside old survey data. Later, when scientists knew exactly what to look for, Tess watched again and built a longer view of the comet's brightness. That is one of the most cinematic parts of modern astronomy. Discovery does not only point forward, it points backward. Once an object is identified, archives become time machines. The comet was there before we named it. We simply had not learned how to see it yet. Test data allowed researchers to assemble a long motion sequence. The comet appeared as a bright moving point while the background shifted around it. It was not dramatic in a Hollywood sense, but scientifically, a stable time series can be more valuable than a beautiful image. Those repeated brightness measurements fed back into the rotation story. A comet too small and too distant to resolve can still reveal its spin through light. Every rise and fall becomes a measurement. Every measurement narrows the shape of the invisible body. The hardest question is age. We cannot rewind its exact path for billions of years with confidence. Passing stars, galactic tides, and tiny uncertainties erase the trail. So scientists use clues in its motion and chemistry to estimate what kind of history it may have survived. One clue is velocity. In the galaxy, older objects tend to have more dynamically heated orbits. Over time, gravitational encounters stir them up. That does not give a birth certificate, but it gives a statistical hint that 3I/Atlas may be extremely old. Some estimates place its possible age well beyond the age of the solar system. If that is right, the ice now venting near our Sun may have formed before Earth existed. A small object, older than our world, crossed our neighborhood and briefly became visible. Chemistry is memory. Water ice, carbon dioxide, organics, dust grains, and irradiation products all preserve something about temperature, distance from a parent star, and time in interstellar space. 3I/Atlas is not just moving through the galaxy, it is carrying conditions from its origin. But location is even more difficult. Researchers projected its incoming path backward through the galaxy and compared it with massive star catalogs. The goal was not to find a perfect home address. The goal was to narrow the kind of stellar neighborhood that could have launched it. The path points through a galaxy that is not still. Stars move. The sun moves. The comet moves. Over millions of years, every possible origin smears into uncertainty. Still, the incoming direction can hint at whether it came from a thin disk, thick disk, or older population. To become interstellar, it probably had to be thrown out. A young giant planet, a passing star, or gravitational chaos in its birth system could have kicked it free. That ejection turned a local comet into a galactic wanderer. That is why scientists care about composition so much. If the comet is rich in certain volatiles, it hints at the temperature zones where it formed. If its dust behaves differently, it hints at processing. Every measurement becomes a clue to the architecture of an unseen planetary system. There will probably never be one clean answer. The story of 3I/Atlas is statistical, layered, and incomplete. But that is normal for astronomy. We build truth from overlapping constraints, not from a single perfect photograph. For billions of years, 3I/Atlas likely crossed dark regions between stars, warmed only by faint radiation and struck by cosmic rays. Its surface would have been processed, hardened, and altered long before the sun touched it. That long exposure matters. Cosmic rays can change the chemistry of surface layers, building complex compounds and dark crusts. Then, when a comet finally approaches a star, that crust cracks, exposing fresher material underneath. The sun may not have been the first star it passed, but close stellar encounters are rare. Most of its life was probably spent in emptiness. That makes the brief heat of perihelion a violent interruption after an age of cold. Near perihelion, sunlight became a furnace. Ices that had slept for eons began to sublimate. Dust lifted. Jets formed. The comet woke up not because it chose our system, but because physics gave it no option. And now it leaves changed. It entered with one surface state and exits with another. Some mass is gone. Some spin energy has shifted. Some layers have been stripped back. The object escaping into the dark is not exactly the same object that arrived. Before fully fading from the story, 3I/Atlas passed relatively near Jupiter in 2026. Not close enough for capture, not close enough for catastrophe, but close enough for Jupiter's gravity to tug the path slightly. Jupiter dominates a huge gravitational neighborhood called its Hill sphere. Passing near that region is like brushing the edge of a giant invisible hand. The comet kept going, but its trajectory recorded the encounter. There was no dramatic capture, no collision, no fragmentation event. Just a subtle bend in an already unbound path. But with an interstellar object, even a subtle change matters because it affects how future astronomers reconstruct where it came from. After Jupiter, the geometry becomes less favorable and the comet grows dimmer. Instruments will keep squeezing data from it as long as possible, but the direction of travel is settled. 3I/Atlas is returning to interstellar space. So why did this object matter so much? Because it turned a rare flyby into a full system test. Discovery surveys found it. Archives recovered it. Spacecraft repositioned. Telescopes measured chemistry. The scientific machine worked. And here is the unsettling part. Interstellar visitors may not be rare at all. They may be everywhere, crossing the solar system constantly, too small or too faint for us to notice. 3I/Atlas may not be exceptional because it exists. It may be exceptional because we caught it. The next generation of surveys will change that. Wider fields, deeper exposures, faster alerts, and smarter software will turn more of those invisible crossings into discoveries. The age of finding one interstellar object every few years may be ending. Once we find enough of them, the question changes. We stop asking what one strange object means and start asking what the population means. Sizes, colors, volatiles, speeds, and arrival directions become a census of planetary systems beyond the Sun. Eventually, we may not only watch one pass, we may intercept one. A spacecraft waiting in deep space, ready to launch toward the next incoming target, could turn a fleeting point of light into a close encounter. The lesson from 3I/Atlas is simple and enormous. The galaxy is not separated from us by a wall. Pieces of other systems are already passing through our own. For a moment, one of them became bright enough to study. Now the visitor is leaving. It will carry our sun's imprint on its surface and our measurements in our archives. We will not see it return. But the next time a point of light moves the wrong way, we will know what to do.